So I'd like to sort of review related rates. And related rates is essentially exactly what it is. You are, in fact, relating rates. So it's very specific in terms of what it's called, and it can actually help us understand what we want to do. We want to relate rates of change. So in this particular example here, we are told that we're essentially told that a spherical balloon is being filled with water at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when its radius is 25 centimeters? So it's very helpful. It's very helpful to actually draw a diagram of what is going on. So if you were to do this here, you'd understand, okay, we have a balloon, it's being filled with water. So you can somehow imagine that we have something of a faucet here, and the faucet is essentially pouring water into this balloon that we have. And this balloon, it's you want to think about these you want to think about these shapes, although that's not a spherically accurate balloon, but you want to think about these shapes in terms of geometric shapes that you already know of, to actually understand how you can somehow relate geometry with rates of change, with related rates. So the idea here is to understand that we have a spherical water balloon. It's being filled with water at a rate of 100 centimeters cubed per second, and we're asked how fast the radius of the balloon is increasing when its radius is 25 centimeters. So we immediately understand that since a balloon is a three-dimensional object, we are in fact dealing with a sphere. And characteristic of circular objects, especially a sphere, we have, of course, a radius. And that radius, let me just go ahead and change the color here. So that radius, actually, I don't think blue is a good idea. Let's just go ahead back to black. So this particular radius here, we can call it R. And as more water sort of pours into this balloon, the balloon itself actually expands in all directions as a normal balloon would, in the process of which the radius too expands, in that the radius is also going to increase in proportion with the balloon increasing or expanding. So as water pours, the spherical balloon expands, and the radius, and of course the diameter for that matter, would increase. In other words, it would change. So we want to understand how fast that radius changes when the radius is 25 centimeters. So this last part here is especially important because we're given a scenario on the basis of the information that we have. And the scenario is that, okay, the radius is going to increase, but we want to know how fast the radius is increasing at a particular point in time. So suppose at this point in time, just hypothetically imagine a particular point. Right now, it's, let's say, 4 centimeters. And eventually it's going to expand if it's flexible enough. It's going to expand and then eventually become 25 centimeters. And it wants to know at this particular point in time, when in fact the radius was 25 centimeters, how fast the radius was increasing. You can think of it more contextually as, let's say, a car is driving down the road, and when it's, let's say, when it reached this particular distance, how fast was it going? And that's essentially the same idea that we're applying here. So in other words, we are trying to find the rate of change of the radius at a particular point in time. And that particular point in time is identified by when the radius was 25 centimeters. So first, let's of course evaluate what we're given. We're told that the radius is 25 centimeters at this particular point in time, of which we want information of, and And we're told that the spherical balloon is being filled with water at a rate of 100 centimeters cubed per second. So the idea here is to understand that this is everyday language to say something is being filled. But mathematically, geometrically, you can think of this as the volume is actually increasing at 100 centimeters cubed per second. Um, and in that sense, this is a rate of change. It is, in fact, changing. The volume of the sphere, or the balloon, of course, is changing at 100 centimeters cubed per second. So you could, of course, notationally describe this as dv over dt is in fact equal to 100 centimeters cubed per second. And over here, all you're doing is you're saying that the um, the the volume, the change in volume with respect to time is 100 centimeters cubed per second. As time passes, your volume is also changing, and that change is 100 centimeters per second. So the change in volume is 100 centimeters cubed, and it's happening every single second. So dv over dt is in fact 100 centimeters cubed per second. And you want to find how fast the radius of the balloon is increasing. So you're, in essence, you're also asking for another rate of change. You're asking for the rate of change of the radius with respect to time, which is dr over dt. And dr over dt is essentially what we're looking for. So we're asked for the rate of change of the radius with respect to time. And we're asked for this in a particular moment of time when in fact the radius is 25 centimeters. So you can think of this as all the information that we were able to extract from the original question, and then can we in fact use this information to actually answer how fast the radius of the balloon is increasing. So we're given one rate over here, and we're looking for another rate. We are in fact relating these two rates together to somehow bridge a correlation between both of them. And then, of course, through some deduction, maybe we can solve for dr dt. Now, what I mean by that is, can we in fact look for a formula, either it be v or r, within which we can actually relate both of these rates of change, or relate what both of these rates of change um, in essence are sort of describing. One is describing volume, and one is describing the radius. So can we think of a formula in context to this problem, which can give us perhaps one equal to the other in somehow shape or form? And asking this question immediately brings you to, let's say, the formula for the volume of a sphere. This makes sense in this context. So if you think about a volume of the volume of a particular sphere, you're actually immediately told that the volume of a sphere is actually equal to 4 over 3 pi r cubed. And the idea here is to understand that our volume is now in relation to our radius. And if we take so this is essentially our formula here, which in essence relates one to the other. And the idea now is we want to find the derivative of v with respect to time. In other words, we want to know how much the volume was changing with respect to time. And of course, if we find the derivative on one side, we want to be able to find the derivative on the other side as well. So the derivative of v with respect to time is just going to be dv over dt. And if we find the derivative here with respect to time, if you think about it, we would just pull out a constant, which would be 4 over 3 pi 2 is also a constant. And then we'll multiply that by the derivative of r cubed, which is 3r squared, using the power rule. And you have to think of r as being something of a a composite function, because r is but uh, it is a function of time. And when you think about a function within a function, you think of the chain rule when we're differentiating, of course. And this eventually leads you to doing the derivative of of the outside first, which we've done, and then of course taking the derivative of r, which would be the inside, which is just dr dt. These threes would eventually cancel, and you'll be left with 4 pi r dr dt. So dv over dt is in fact 4 pi r multiplied by dr dt. So we now have the volume and the radius in correlation with each other. That's what we achieved by sort of finding out the formula for a equation which could relate them both. And we've taken the derivative to have a snapshot of time, which can actually tell us, if we were to plug in the values, what in fact this situation would look like. So we are now in the scenario which we want to be in. That is to say, we want to find dr over dt, but we want to do so once we have all the values for the other variables. So we know what dv dt is, and again, the idea here is to sort of plug in all the values that we know to eventually then solve for dr over dt, which will be a concrete value if we do it algebraically. So dv over dt we know is 100 centimeters cubed per second, so let's just call it 100. And it's equal to 4 pi, and then of course we're multiplying by r, which we know is 25 centimeters in the situation that we want to solve for. And let's just call it 25. And of course we forgot to, when we were taking the derivative of r cubed, we want to essentially bring down 3, multiply it by r, and then that would be r squared because we want to decrement the power by 1. That's of course a standard power rule for taking derivatives. And then of course that's 25 squared multiplied by what we had before, which is dr dt, which is of course, if you come back here, what we wanted to solve for. So if you think about it now, it seems as though if we were to isolate dr over dt, since we have, of course, concrete values, we could eventually solve for dr dt. And dr dt can essentially have a value which will essentially be how fast the radius of the balloon is increasing, when, of course, its radius is 25 centimeters squared. So if we were to divide both sides by 4 pi 25 squared, we would do so on both sides, and we would eventually find that dr over dt is in fact equal to 100 centimeters cubed squared, or per, I think it was per minute, over 4 pi 25 squared. And if you were to plug this into a calculator, you would in fact get a decimal number, which closely approximates, I think, I'm not too sure, but this is essentially where you would end up. So again, we evaluated the information that we were given, and we found a formula which relates both of those pieces of information, and we we took the derivative of both sides of that equation because we wanted to find the information, the rate of change at a particular moment of time, which is of course the volume in a particular moment of time. Took the derivative of both sides, solved for what we wanted, which was dr over dt, and with some algebraic manipulation, we were able to come to a concrete conclusion. So let's actually go ahead and look at another question here, which is a little different, but it follows more or less the same pattern. So it says here that a water tank has the shape of an inverted circular cone. It's good to take this in pieces. So if you think about an inverted circular cone, you're actually looking at something that looks like this. And the idea here is to understand what the question is saying in context to the cone. So it's saying that the cone has a base radius of 2 meters. So this would essentially be right here. So you'd have a base radius of 2 meters, and you'd also have a height. So you'd have a height of about 4 meters, it seems. And if the water is being pumped at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 feet deep. So what this is actually trying to say here is that the cone is in fact being filled with water, right? It is being filled with water, and as it's being filled with water, we want to essentially find the rate at which the water level is rising. And you can think of the water level as simply being the height of the water. So as the water increases, or fills the cone rather, of the height of the water level would essentially increase, which would of course be a portion of the original height of the cone. So once we find the rate at which the water level is rising, we want to understand that we don't want to just find the rate at which the water level is rising, but we want to find the rate at which the water level is rising at a particular moment of time. So that particular moment of time would be when the water level is 3 feet deep. So if we were to imagine the water level rising, we want to take a snapshot of a particular moment, which is of course when the water is 3 feet deep. If it rose a little bit more, it probably would have been 4 feet, or anything above 3. But exactly when the water is 3 feet deep, we want to figure out how fast it's rising at that moment. We want to find the height of the water level at that moment. And you can think of it as being the height of the cone um, at that particular moment, but that doesn't make too much sense in terms of what's possible, right? So we mask it in this particular context as water filling up a cone. And you can see here that it's being pumped at a rate of 2 meters cubed per minute. So it seems as though we're given a rate of change, which is in fact 2 meters cubed per minute. And that would be, so you can think about the volume of a cone is being filled. Just in the previous example, as we said that um, the balloon is being filled with water at a rate of 100 centimeters cubed per second, what we actually recognize that it's just the volume of the sphere which is expanding. And here it's just the volume of a cone which is essentially being filled at a particular rate. So again, you have the volume of the cone changing, so you are given dv over dt, which is in fact, you're given dv over dt, which is in fact 2 meters cubed per minute. And you want to find the rate at which the water level is rising when the water is 3 feet deep. So when the height of the water is 3 feet deep, you are essentially looking for dh over dt, which is of course, you're looking for the height regardless, but you're looking for the height at a particular moment of time. You're looking for the rate of change. And so you're looking for dh over dt. So you're given dv over dt, you're given the height at which you want to figure this out. And well, the height normally is 4 centimeters, but dh over dt is essentially what you want when the height of the water is essentially 3 feet. So essentially the goal now is to sort of relate the rate of change which we're given with the rate of change that we have, very similar to the previous problem, and essentially solve for dh over dt in some shape, manner, or form, so that we can actually have dh over dt as a concrete value. So first and foremost, what is the equation which can somehow relate dv over dt over dh over dt, or really relates some kind of equation which relates volume and height. And if you think about it, if you were to do a little research, you would eventually arrive at the volume of a cone, which makes sense in this context, which is actually equal to so the volume of a cone is actually equal to pi r squared h over 3. And the idea here is that we recognize that we have volume on one side, the radius on the other. This makes sense. Or not the radius, but the height. So we have a relationship going on here. We've related two different rates. One rate we're given, and the other rate we actually want to solve for. And of course, if you follow a similar procedure as we did in the previous problem, you'll eventually take the derivative of both sides. So here, where we had the volume equal to 4 over 3 pi r cubed, what we did was we took the derivative of one side and the other, and then we solved for what we wanted. But in this case, if you remember, we're eventually going to take a derivative of r squared. Now, if you think about it, r squared, the derivative of r squared, you would first use the power rule to actually bring down the 2, have the r there, decrement the power, which would just be 1, and multiply by the inside function, which is r. So you actually be left with this as your derivative for r squared. So you'd take the derivative of one side, which would be, you'd get dv over dt. And you take the derivative of the other side, you'd get pi is just a constant, pull that out. And then when you get to the derivative of this, you'll get this as an answer, and then you'll take the derivative of this as well. But what you want to recognize is that while you have the radius, which is of course 2 meters, I believe, you don't in fact have the rate at which the radius is changing. So this is sort of a multi-layered problem. And the problem is that you want to somehow have dH over dt, the thing you want, unsolved for, or in other words, you don't want dH over dt to have a concrete value yet, but you want everything else to have a concrete value, because everything else is eventually going to be equated to dH over dt in some way, shape, or form, which would, of course, reveal the value of dH over dt. So, so in the process of which you'll actually have to have a value for dr over dt, something you don't have, and something you perhaps would have to go on a tangent to find. And it seems as though you're looking at another problem here entirely. So is there some way we can actually omit the r without actually just blatantly taking it out of our equation? We can't change the formula, but perhaps we can change the way we express r squared. So this is where we get into what is called similar triangles. So if you actually look at this particular cone here, you can imagine this as being a triangle, right? And perhaps more of a mathematically rigid way of expressing this. And if we were to sort of take this off to the side here, you would actually recognize that we have a triangle here. And the triangle, we said, would have, since we took half of the cone, the length of this triangle on this side here would be 2 meters. And the height would actually still stay the same. So you'll still have a height of 4 meters. And then, of course, at any given point in time, you'll actually have your water increasing. But the idea to recognize is that when the water is increasing here, you'll actually have a radius, of course, and of course you'll have a height associated with this water level at any given moment of time. But the key thing to realize here is that as your water level increases, your radius and height will actually be in proportion to the radius of your original triangle, and of course, the side of your triangle, the height of the original. So they're sort of increasing in unison in the sense that they are proportionate. And so in some sense, you can say that um, that 2 over 4 is actually equal to r over h. Or in other words, if you were to simplify this down, you can say that 1 over 2 is actually equal to r over h. And if you were to solve for r, your h's would cancel out here, and you'd get h over 2 equated to r. So your radius is, in some sense, h over 2. So you can actually go back to your original formula here and actually substitute h over 2 wherever you find r, which is, of course, your radius. And you wouldn't actually be putting something there which is not itself equivalent to r, because, of course, r is equal to h over 2. So we say that v is equal, so we could say, if we were to go back to our regular color here, we could say that v is in fact pi h over 2 squared h over 3, right? And this essentially omits the r in some sense, and we are now only dealing with one variable, which is good. So you can actually, if you were to simplify this a little down, if you simplify this a little bit, you would actually get pi multiplied by h squared over 4 times h over 3, which would, of course, simplify down to being pi h to the 3rd power over 12. So whereas we had this original formula before, we are now dealing with this formula, which is, of course, in some sense equivalent to the original formula, but with the r absent, so that we actually don't, so that when we take the derivative of both sides of this formula, we actually won't be dealing with an r, which means we solve our original problem of not having to find the rate of change of the radius with respect to time, so as to get or attain our rate of change of the height with respect to time. So if we were to take the derivative of both sides here, we would have dv over dt on one side, essentially equated to pi over 12. We're going to pull that out, multiplied by the derivative of h to the 3rd power, which we're going to bring down to 3. We'll have an h decrement by 1 multiplied by dh over dt, of course. And now it's essentially much better to solve for dh over dt, the original thing that we wanted. So if you think about it, you can actually just plug in your, so you're now in the scenario where you're figuring out what in fact the height is. And so you can plug in your height, which they said at that particular moment you wanted, which is 3 feet. So we'll have 3 squared here, multiplied by dh over dt. So now you can see that everything else has a value. In fact, dv over dt has a value as well, because if you remember back here, dv over dt was 2. And I think it was 2 meters cubed per minute, but we'll just write 2. And so if you were to solve for this, you can see here that everything else has a value. And you are then, of course, solving for dh over dt. It becomes possible. And so if you were to do this here, you'd get pi over 12 multiplied by, you'd have 9 here. You can actually just, I think what you can do is you can sort of simplify this a little bit. This can go to 4, so you'll have 2 is essentially equal to pi over 4 times 9, right? Because this would go to 9. And then you'll have dh over dt. And if you divide both sides by 9 pi over 4, you'd actually, so if you were to divide both sides by, if you were to do some arithmetic here and divide both sides by 9 pi over 4, you'd actually have 4 times 2 over 9 pi, which would equal dh over dt, because of course we're taking a fraction, we're dividing both sides, and so when we divide this by this fraction, we're actually going to take the reciprocal, multiply by the reciprocal, that is, and then we'll have 8 over over 9 pi equal to dH over dt. And of course, if you were to plug this into a calculator, you would get a more exact answer. But this is in essence what we want to take away. And so, you're looking at related rates and you're thinking, what do I do? Well, the answer is draw a diagram and look for what you're given, right? Are you given a rate? And if you are in fact given a rate, what rate are you not given, right? And look at the rate that you're given and look at the rate that you're not given and somehow relate both of those rates. And once you relate both of those rates in, of course, an equation, can you in fact take the derivative of both sides of those equations and then, of course, solve for the rate that you want to attain? And in doing so, you want to make sure that everything else has a concrete value so that the rate that you want can eventually have a concrete value once you, of course, perform some algebraic manipulation. And the formula, the original formula, which is going to lay the foundation for the entire problem, is essentially going to be directly related to the geometric shape described. So here you can clearly deduce that we're looking at the volume of a cone is being filled. And previously we clearly understood that we're filling a balloon, and there is in fact a formula for the area of a balloon, or the volume of a balloon rather, or the volume of a sphere rather. And then of course we imposed the same process. So this is related rates, and hopefully that was helpful to some degree.